Hello, everybody. My name is Alex. I am an instructor of the GMAT from Manhattan Prep. Happy to be here with you today. Today is about advanced number properties. However, it is not about the properties of numbers that are the most advanced. I don't know if everyone knew this, but math is really big. There's a lot of math out there. People spend their whole lives digging deeper and deeper into math and coming up with the craziest number properties out there. And when it comes to the GMAT, it's about noticing and using the number properties that come up over and over and over again, the ones that are really helpful to know for this test. And being advanced at those means that you recognize them as close to instantly as possible. So to start, we are going to try some really quick math, some quick quant, some quick number properties. Now, let's move forward, and I'm going to show you 4 questions, and I'm going to give you 2 minutes to solve all 4 of them. They're not full questions. I'm only going to ask you to do 2 things. The first thing is going to be to tell me, what is this problem testing? What part of number properties is this problem testing? So Jaideep's got a great question, like what comes under number properties, right? Divisibility in primes, evens, odds, positives, negatives, consecutive numbers, exponents a little bit in there, combinatorics and probability, although we're not going to talk about those much today. So take a look at these 4 questions. I'm going to give you 2 minutes to let me know, first of all, what is this problem testing? So what part of number properties? And then it's just one statement. And the question is this statement sufficient to answer the question? You don't need to put your answers in chat just yet. We're going to go through them one at a time, and I'll ask you for your answers there. But write down your answers, all right? 2 minutes for these 4 questions, really quick. On your mark, get set, go. One minute left. Time. That's 2 minutes. Not a ton of time to answer 4 different questions, right? This is advanced GMAT number properties. This is figuring out the number property as quickly as possible, being able to use it to answer the question as efficiently as possible. So take a look at just this first one. And as we go, we're going to be talking about the code. I'm going to mention the code a lot. The GMAT is a very specific subset of all of the math that there is in the world, right? So the quant section, it's not testing all math, it's testing a very, very specific subset. So they use and reuse the same things over and over and over again. And that's what the code is. It's being able to see through the question into the specific GMAT language that they want to test you on. So today we're looking at number properties. Those number properties are pieces of the code. So take a look at this first question. Let me know in the chat. What number property is this question really asking about? We've got the variable m, we've got m squared, so exponents are there. We've got the word divisible, so a lot of people are thinking divisibility, getting a lot of those in the answers. So is this a divisibility question where we're worried about like the factors of m? Not really. They put divisibility on the surface, but if they're asking if this thing is divisible by 2, then they're also really asking if this is a odd even question. Yeah, so odds and evens are kind of tied into divisibility because that's what makes it odd versus even if it's divisible by 2. But being able to see this as, is this divisible by 2? Is this even? Can save you some thinking on this test, right? Being able to look past this and think, oh, okay, it's just a question about odds versus evens. And I know a lot about odds and evens. That's going to help me to answer this question. And then, yeah, a lot of people have said this is not sufficient, right? And if you look at these, each of these questions, that's the other question, right? Is this statement sufficient or not? Now, as I talk about the code, I'm going to be talking about using that code, using that theory to save you time. When you don't have the code, you got to do what we call testing cases, right? And this comes up on data sufficiency a lot, where you just test one case and a second case, and if you can get 2 different answers, then you're good to go. That means it is not sufficient. So in this case, this is what testing cases might look like, right? We're going to think of a value for m squared, think of a value for m, and then ask the question, is m even? Because that's really what this odds evens questions is asking, right? Is m divisible by 2? Is m even? So case 1, if you think of something that is divisible by 2, because that's what the statement tells us, then m, the square root of m squared, is not divisible by 2. And that gives us a no answer. So then we want to think of a yes answer, and this might be actually easier to think of, where m squared is 4 and m is 2. Once we have a no and a yes, that means we know that this statement is not sufficient. So can you look at this statement and this question and answer this without testing cases? Yes, it is possible. If you know the code well enough, if you are confident enough in your odds and evens to look at these 2 statements and think about what they mean, then you can answer this without testing the cases. But until you get there, testing cases is where you want to be, right? You always have that as kind of your baseline. Question, if m squared is divisible by 4, would that be sufficient? Yes, because if m squared is divisible by 4, then the square root of that would be divisible by 2, I think. Let me know if I'm getting that wrong. But if there's a 4 in there, you square it, or you take the root, then it would be divisible by 2. 2 for m squared. Well, what if m squared was 12? That's divisible by 4. The square root of 12 is not divisible by 2. So no, divisible by 4 wouldn't necessarily work. Still would be not sufficient, because we'd have some that work and some that don't. So what Jaideep's kind of highlighting here is that when they give you a statement, that's where you want to be starting from. If you're testing cases, start from the statement. Think of possible m squareds rather than possible m. I was just trying to think of something that I couldn't take the square root of, so I thought of 12. Okay, on to question 2. Let me know, again, what number property is this really testing? And in the same chat, if you can, whether or not this is sufficient or insufficient. Sorry, we're doing the one on the right now, top right, question 2. Yeah, this one is a little bit more on its face, right? The last one, the odd even thing, was kind of tucked in there. And this one, greater than 0. Whenever we see greater than 0, less than 0, you might want to think about odds or positives and negatives. And again, depending on how confident you are in your rules about positives and negatives, this question can be pretty quick to answer, right? If not, then you might need to test some cases again. So again, I'm going to show you what testing cases might look like. We're going to pick something for R, pick something for S, and then see if that makes T positive or negative. But one thing about number properties is that you can test individual numbers like we did in question 1. But if you know that we're dealing with the theory, you can also just test the theory. So if you just test with the properties of the numbers, it can be a little bit faster, right? If we know we're dealing with positives and negatives, we can just think, okay, what happens if R is positive and S is negative? In that case, S obviously would be the same. So S would be negative on top of T. And if that's going to be a positive result, then both top and bottom have to be a negative. So that makes T negative. In case 2, if R is negative and S is positive, then T would have to be positive as well. So we have 2 different cases that both work, and one's a no and one's a yes, making this not sufficient. But again, you can look at this original question and see we're dealing with positives and negatives. What do I know about R over S if it's less than 0? They've got to have different signs, right? If they're both positive, it's going to be greater than 0. If they're both negative, it's going to be greater than 0. So one of them has to be positive, one of them has to be negative. So they're different signs, and it's the same but opposite for S over T, right? If that's positive, then they have to have the same sign. So if R and S are different and S and T are the same, then whatever S becomes is the same for both. So then R would be different from S, which means it's different from T. But still, we have 2 options there, right? If R is positive, T is negative. If R is negative, T is positive. 2 different options, meaning not sufficient. Okay, on to 3. spoiled this one a little bit. And this one we have an exponent. So you might think, oh, what does this mean? What do I know about exponents? We also have a less than 0. So definitely dealing with positives and negatives in some way. The odds and evens a little bit tougher to see here, but we'll see why we're actually dealing with odds and evens as well in this question. So let me know in the chat again, is this sufficient or no? All right, getting more not sufficients here. And again, we can prove the not sufficiency by getting 2 cases, right? Would look like this. We have an A and a B. How do we get B to the A to the 8th power less than 0? Well, we can try A is 1 and B is -1. That works. A is greater than B. We can keep B the same, make A a different value to also have a valid case in which A is not greater than B. And there we go, not sufficient. But again, with advanced number properties, we want to be able to see past this, right? So just looking at B to the A, if this integer to this other integer power is negative, what do we know? We can tell from our cases that in both of the cases, B is negative. And that's one thing that we know, right? To put an integer to some other power and have the result be negative, the integer, the original integer, needs to be negative. Exactly, B is negative. Beyond that, I asked the chat, what do we know about A? We know that B has to be negative in order for this to be a negative result, B to the A. What do we know about A? Yeah, we know 2 things, right? We know A can be positive or negative, but we also know, yes, that A has to be odd. It can't be even, because taking a negative number B to a even exponent will get rid of that negative, right? If you square a number, it will become positive, no matter what it is, positive or negative. So A could be positive, could be negative, but it has to be odd. And that's how this question is actually also testing us on odds and evens. Because now we know that, right? Based on statement 1, we know that B has to be negative because any negative integer taken to a power, or for any integer taken to a power to become negative, it needs to start negative. If we take any positive number, 2, there's no power, there's no integer power we can put that to make it a negative, right? Even if we make it like to a negative power, it becomes 1/2. So it's still positive. So if we want this result to be negative, which is what statement 1 is telling us, we need B, the base, to be negative. And then we need A to be odd, because if we take even a negative number like -2 and take it to an even exponent, it's going to square it, which means we're going to lose that negative and it's going to become positive. So knowing that didn't necessarily help us to answer this specific question of whether statement 1 is sufficient or not. But imagine another statement, or combining the 2 statements for that final step. Not just knowing that B to the A is negative, but knowing that B has to be negative and A has to be odd. You can bet they're going to give you some kind of other statement there where knowing that A has to be odd answers the question. So being able to see this theory, not only does it help you to answer questions like this a little bit faster, like in question 2, but it can give you more information than just having the statement or just having your cases. All right, on to statement 4. What is this testing? What number property? And is this sufficient or no? All right, getting some answers in. Odd even, definitely on its face is right there. We've got J plus K is odd, so we're going to have to deal with odd in some way. But we also have factors, and it's a little bit harder to see. It doesn't say it, but we do know that J and K are positive integers. J is equal to 16 over K. So we could rewrite that J times K is equal to 16. We have two positive integers that multiply to get 16. Then we know that J and K are both factors of 16. In fact, they are factor pairs. So if we know that they are factor pairs, then we know that these options for J and K, there are only 3 of them, right? It's 1 and 16, 2 and 8, 4 and 4. Those are the options for J and K. So it's a sneaky divisibility factors question. Now we do have to deal with odd in statement 1. Statement 1 says J plus K is an odd integer. So we've got only one factor pair that is odd, 1 plus 16. That sum is going to be odd, which means 1 and 16 is our answer, which means statement 1 is sufficient. Except it's not sufficient. And the chat is kind of torn between sufficient and not sufficient. So even when you get to this point, you think, oh yeah, there's only one option, 1 and 16. But it could be, well, it can't be negative, because they tell us they're positive integers. But yes, J can be 1 or 16. The question isn't what are the two values of J and K in any order. The question is, what is the value of J? And J could be 1 or J could be 16. So there's a reason I had you do these questions ridiculously quickly, right? One is to highlight the helpfulness of knowing the code and knowing these number properties. And 2 is to force you into traps like what a lot of people fell into on question 4. It's very subtle, and it's one of those things that the GMAT loves to do. And the more questions that you do, the more of these little traps that you see, the more wary you're going to be of them. You're like, man, I forgot the question that time. I'm not going to do that again. The next time you see a question that's similar to this, you're like, oh, I remember what happened last time. They're not going to get me again. Not again. So all 4 of these end up being not sufficient. And all 4 of them are testing number properties. And some of them, it's a lot clearer, like definitely that's what we're testing. Some of them, you don't know until you get into it, which number properties are helpful of knowing. So what's your goal? Your goal is to be familiar with these number properties. Be familiar enough that when you see a question like this, you are able to look past the specifics of the question and use those number properties to help you answer quicker, right? Maybe you avoid testing cases altogether because you can see the theory behind the question. So how do you get there? Well, one way is that you have to learn these codes, right? The first time you see it, you're not going to know it. If you see a code that you didn't know, flashcards are a great way to memorize these things, right? You see a question like this, oh, I didn't actually realize that this one was testing me on positives and negatives. I was just testing some cases, but from now on, I'm going to know what to do when I see this thing. So on the front of your card, it's going to say, when I see this. And you don't want to put the whole question. You just want to put the thing that is the code. In this case, we're multiplying or dividing to get a positive or to get a negative. So when you see that, what are you thinking? Obviously on the back, you're thinking positive, negative. That's the first thing, is that I am thinking positive, negative. That's where my brain wants to go. And then for each of those options on the front, you write down, what do I know about S and T? S and T have the same sign. If they multiply or divide to be positive, they have the same sign. If they multiply or divide to be negative, they have different signs. You want this to be as close to immediately accessible as possible. So if you haven't seen the code before, make a flashcard. Even if you have seen the code before and like you know in your brain that that's how positives and negatives work, if you're not instantly coming to these conclusions, like, oh, they must have the same sign or they must have different signs, the flashcard is still helpful because you want this to be like flash memory, right? You don't want to spend any extra time thinking about the theory behind S over T is greater than 0. You just want to be able to make that instant lightning fast connection. Great question in the chat. Why are Manhattan Prep Quant cats so impossible to complete in 62 minutes? There's a couple reasons for that. One of them is that you kind of want your practice to be, if anything, a little bit harder than the real thing. It's better than the alternative of thinking it's going to be really easy based on your cats and then going into the thing and being surprised at how hard it is. The other thing is that it's tough to make cats. You want your cat to be able to cover anything that could possibly be on the test, right? You don't want there to be things that aren't covered on this cat. So you make the cat to cover all of these edge cases. And so sometimes you roll the dice on this cat and you end up getting a bunch of edge cases in a row. And it's not necessarily harder, it's just weirder. So you can come across some weird stuff. Any of it could show up on testing, but we just want to make sure that you see everything the GMAT has to offer. Great question. So let's jump into a real like GMAT styled question. Take a look. I'll give you a minute and change to solve this one. Go. When you get your answer, put it in the chat. All right. So I love this question because you always get some people who answer like incredibly quickly and some people who take a bit longer to get there. But there's a lot to unwrap here, my favorite thing about this question is this figure, x cubed minus x plus 1, actually has a lot going on. If you take out the x, like if you kind of ignore this plus 1 for now, and just look at x cubed minus x, you can factor out the x. So we have x times x squared minus 1. And then you can notice we have x squared minus 1, which is the difference of squares. So we can factor that again. So x times x plus 1 times x minus 1. And then you can reorder these three and see that, oh, it's x minus 1 times x plus 1, which is 3 consecutive integers. Exactly. And you can notice this, right? You can see x cubed minus 3 and now know, oh, that's 3 consecutive integers. That's another code. You can learn that number property. And if you have 3 consecutive integers, you know that one of them is going to be even at least, and one of them is going to be divisible by 3. You take any 3 consecutive integers, right? 2, 3, 4, that's got a 3 in there. 26, 27, 28, that's got 27 in there. Always going to be divisible by 3 when you multiply them together like we're doing here. So if we know that x cubed minus x is divisible by 3, then when we plus 1 to it, we're just adding 1 to that remainder. Right? You take something that's divisible by 3, like 6, and you add 1 to it, it becomes 7, and now the remainder when you divide by 3 is 1. So B is our answer. So that is one thing I love about this question, is that you can look at this, know the code, see that we've got consecutive integers here that we're multiplying together, and then know that that is divisible by 3. But the reason I really love this question is because you don't have to do any of that. Because this question is saying, given any integer x, what is the remainder? This is not a data sufficiency question where we can have a lot of different answers, right? It's problem solving. It's multiple choice. One of these answers is going to be the remainder no matter what we put in there for x. So you can know the code here and see the consecutive integers, but really this is a choosing smart numbers problem. A problem where if you can pick a good number to put in there, the question's going to get a lot easier. And the good news here is that any number will work. Any integer we put in there for x works. So you can put anything in there. You can put 0 in there, 1. If you put 2 in there, then 2 cubed, let's say, yeah, x equals 2. 2 cubed minus 2 plus 1. 8 minus 2 is 6, plus 1 is 7. And the remainder is 1 when we divide by 3. What if x is, yeah, negative? Negative 2 cubed plus 2 plus 1. We cube that, it's going to be negative 8 plus 2 is negative 6 plus 1 is 5. Oh, that ends up being 5. That's why people are bringing it up. If it's negative, what am I missing? Negative 2 cubed, negative 8 plus 2, negative 6 plus 1 is negative 5. Is it a remainder thing where you can't have a remainder if it's negative? So on the GMAT, you got to have positive integers to get a remainder. There's your takeaway. If there weren't a rule about that, then we would have said something like, given that x is a positive integer. But that's a great GMAT takeaway, is that for the GMAT, to have a remainder, you've got to have a positive number. There might be some far off version of imaginary math where you can have that, but not in the GMAT, at least. Great question. So that's your two takeaways, right? Is first of all, more importantly, notice that this question, any x that's positive for the GMAT sake, will work when you plug it in here. And it's going to give you the same answer, which means it doesn't matter what you plug in. You can just pick a number. Pick 0, pick 1, put 2 in there, and you can get the answer. It's going to be the same for every single one because this is a problem-solving question. The other takeaway is this is another code, right? This is a code that you can know. If you see x cubed minus x or any variable in there, you can think, oh, that's consecutive integers. I now recognize that I can take out the x. Then I have a difference of squares, and you don't have to actually do all that work. You can just know if you have this on a flashcard. So this is another piece of code that you can see. There's another piece of code here, right? When the question's saying, what's the remainder when divided by 3? And the thing that they give you is divisible by 3 plus 1. If you know that that divided by thing has to match, that's no remainder. And then whatever they add to it is your remainder. So this is what number properties should look like for you on the GMAT. You know some things. If you look into deeper number properties, you're going to start seeing things that you didn't know, right? For those things, if it's something that comes up on the GMAT a lot, like consecutive integers shows up, then you can make a flashcard for that and start to know these things just like nothing, just like right off the top of your head. Okay, let's look at a little bit of a harder question. I'll give you a minute and a half. Go. All right, that is 2 minutes. Give you a little bit of extra time. This is a tougher question. A lot of work that can be dumped into this question. And Ansh in the chat has come up with the perfect number property for this. That if you know this number property like the back of your hand, this question gets pretty easy. What are the odds of this exact number property coming up on the GMAT? Very low. right? It would really help you on this specific question, but is it one of the ones that comes up all the time that, is really going to make your money's worth? Not necessarily. So before we talk about that property, let's talk about how you can solve this question without that property. Right? There's a lot we can do here without really even talking about what the math is actually saying, right? This question is kind of weird. Does the integer k have a factor p such that 1 is less than p is less than k? There's a way to rephrase this. If you don't have that way, then what do we know? We know that k is an integer, and we've got one relatively easy statement and one very complex statement. 4 factorial, that one we can kind of figure out, right? We know that k is greater than 24. Statement 2 is bonkers. There's a lot going on. 13 factorial is an incredibly high number, and k is going to be greater than or equal to that, plus 2. So we know that k is greater than this incredibly high number, which is basically what statement 1 already told us, right? If statement 1 says k is greater than 24, statement 2 says the same thing, but also gives us more. We can cross off some answers. Whenever you have one statement that basically takes over the other statement, it says the exact same thing, but then gives you more information, you can cross off that smaller statement. Because if A were the answer, then statement 1 would be kind of superseded by statement 2. Statement 2 would also be sufficient if statement 1 was sufficient. So we know that we can cross off A. We also know that we can cross off C, because in order for C to be right, the two statements would need to come together, right? They're each kind of bringing their own thing into the equation. That's what C is. We need both of them. But in this case, we don't need both of them, because if we have 2, we know that 1 is, it is already the case, because 2 is true. It doesn't mean that 2 is definitely right. We can't just circle B and move on, but we know that it can't be A or C. So this is one thing to look out for, right? When you have a statement that supersedes another, a statement that kind of takes over, says the same thing as the other statement with extra information. Now then, when we actually get down to solving this question does have a rephrase that Ansh very well put into the chat, asking if k is prime or not. That is the real question here. Is k prime? And you can look back and see that that's basically the definition of a composite number, right? A number that has a factor that is not itself or 1, that is in between 1 and itself. So that's the question. Is k prime or is k composite? We know that it's greater than 1, so it has to be either prime or composite. Now you can get there by thinking about some values that would work, some values that would have a p or not have a p. Like 5 is prime, so it doesn't have that factor. 10 is not prime, so it does have that factor, a couple of them. And then you can get to prime that way, but it's another piece of code that you can know. We cross off A and C, again, because we know that statement 1 just says k is greater than 24. Statement 2 says that k is greater than or equal to this enormous number, whatever it is, 13 factorial. It's huge. So if statement 2 is true, then we know that statement 1 is also true. And that's why A can't be the answer here. Because if A were the answer and it was sufficient to know that k was greater than 24, then 2 would also be sufficient. Because with 2, we also know that k is greater than 24. So that's why we can cross out A. But in actually solving this, we don't know yet if 1 is sufficient, right? Because it could be that both answers are sufficient. We can't cross off D yet. But if k is greater than 24 and the question is k prime, we don't know. right? Because it could be prime or it could not be prime. There's a lot of numbers that are greater than 24. So we don't know, not sufficient. At this point, you can cross off A, D. C has already been crossed out because statement 2 takes care of statement 1. If you're stuck between B and E, B is the right answer to guess, because a lot of students look at this and they go, I don't know how to deal with that. And our initial reaction when we see something we don't know is to think, nobody knows, right? There's no way to do this. And so they make E that kind of trap answer when you have the really ridiculous looking statement 2. So B is a good guess here. Now, how do we actually solve this, right? Well, there's a reason why we're going from 13 factorial plus 2 to 13 factorial plus 13. And if we think about that range, there's not that many numbers within that range, right? It's some huge value plus 2, and then plus 3 would be in there, and then plus 4, all the way up to 13. So if we think about what these values could be, right? K could be the lowest value here, which is 13 factorial plus 2. The question is this prime? Well, we know that 13 factorial is just 13 times 12 times 11 times 10. So we're just multiplying all of these integers together. And so 13 factorial itself is not going to be prime because it's made up of all those factors, right? 13 times 12 times 11 times 10. If we add 2 to the mix, well, we know that this number is already multiplied by 2. So 2 is already a factor of 13 factorial. If we add 2 to the mix, then that number that we've made is still divisible by 2, right? We had a value that was divisible by 2, and we added 2. So we had an even number, and we added 2, and it's still even. It's still divisible by 2. So by adding that number that's already a factor, we know that this value for K is divisible by 2, because it was divisible by 2, and then we added 2. And the same thing is true for adding 3. We knew this number was divisible by 3, and we added 3 to it, which makes it another divisible by 3 number. And this continues all the way down the line, and that's the reason why they stopped at 13. So we know that all the numbers in this range are all divisible by whatever thing we are adding, because 13 factorial is divisible by everything between 1 and 13. So this ends up being sufficient. Answer is B. So most everyone got this one right, but some people got it right a lot faster than others. So again, if you're like Ansh and you know this theory, if you know that, what was it? In everything from n factorial plus 2 greater than or equal to n factorial plus n. So if we had k in between there, then you could know, I wrote this wrong. You could then just know, like, all these things are not prime. They're all divisible by the thing that we're adding. Is that super helpful for this test? It's helpful on this specific question, but again, the odds of it coming up, very, very low. So this lesson, again, it's not about the most advanced number properties. Like, this is a very advanced number property. It's about being able to see the properties when they ask about them, especially the ones that show up again and again and again. So with that in mind, a little mindful of time here, we're going to do one more question, and I'm only going to give you 1 minute to solve it. See how quickly you can possibly answer this question. On your mark, get set, go. All right, thank you for getting your answers in so quickly. Obviously, if you take 2 minutes to answer this question, it's not the end of the world. Right? You can take 2 minutes on a couple of quant questions and be okay on this test. But I wanted to push the timing here for this reason, right? This is what this lesson is all about, is about being advanced enough with your number properties that you can solve questions like this faster than most people, right? Most people, when they see this, maybe they think about the values of evens and odds. Maybe they end up like testing a bunch of cases, right? Like, can I think of some value for A and for B, and then see if this thing is even to see if it's valid? And then I can answer the whole question, which is A, B odd, question mark. And like we did at the beginning of this lesson, do a bunch of testing cases and maybe get to the answer. The goal here is to be able to translate this, right? Know the code. We're asking about even and odd. Obviously, we have A and B. They are positive integers. And the question is A times B odd? It's a yes or no question. So like somebody put in the chat, Karan put in the chat, question is asking if both A and B are odd, right? Because that's what we would need in order for A times B to be odd. These two positive integers, they would both have to be odd. So that's a rephrase of the question. Then we get to statement one. And if you don't want to go in and like think about what the actual values of A and B could be, you can think about the theory, right? What do we need to have two values that when we subtract them, it ends up being even? We know that it's either going to be an odd minus an odd or an even minus an even. Those are the only two ways we can get an even. So we have 3A and 2B. Do we know if either of them are odd or even? Yes, we do. We know that 2B has to be even because we're multiplying it by 2. Whether B is odd or even, it's going to end up being even when we multiply it by 2. So if we need these to be the same, like even, even, odd, odd, once we know 2B is even, then we know that 3A is even. So that's what statement one is really telling us, is that 3A is even. And if we know that 3A is even, then we know that A by itself is even, because we have to have an even, multiply it by an odd number like 3 to get an even value. So we know that A is even, and we know that we would need both of them to be odd for A times B to be odd. So AB is going to be some even number times B, and that's going to end up being even. Any even times anything is going to end up being even, any integer. So this is sufficient. It's sufficient to know that one of our two values, A or B, is even. So take another look at statement two. If you didn't think about statement two in that way, think about it that way now. And if you want to change your answer, send me your new answer. If we know that 4A plus 3B plus 1 is odd, well, we're going to take whatever 4A plus 3B is and add 1. And that's going to change the polarity, right, between odd or even. So 4A plus 3B is equal to some odd number minus 1, which means that 4A plus 3B is even. And we know that 4A has to be even because we're multiplying something by an even number, which means 4 times A is going to be even, whatever it is. And again, if we want this thing to be even, we need to have the same sign for both of our things that we're subtracting or adding. In this case, we're adding. So if 4A is even, 3B also has to be even. So 3B is even. Now we know that, which means, again, we know that B itself is even, which means A times B is going to be A times an even which is going to give us an even number. So this is also sufficient. And D is our answer. So again, if you take 2 minutes to answer this, it's not the end of the world. But I want you to challenge yourself to become the most advanced with number properties possible. This question really lets you know what advanced number properties is all about. Your ability to look at this question and look at these statements and think not about the exact numbers of A or B, but just to visualize the theory behind it. What do I know if 3A minus 2B is even? I know that they're both odd or they're both even. And I know that 2B has to be even, which means 3A is even. So without coming up with any possible cases for A or B, we can figure out that A has to be even, which is enough to answer this question. So difficulty is an interesting thing on number properties questions, because if you know the number property, the question gets a lot easier. So you end up having these big splits of difficulty between people who know the properties and people who don't. This question, I would say, if I gave you all 2 minutes or 3 minutes, most people would be able to get this one right. Does that make it an easy question? I don't think so, right? This test is full of things that you want to be able to get right as quickly as possible. So challenging yourself to do this question in 1 minute, like I did, that's really hard, which makes this a good practice for number properties, right? Because you want those number properties to just be right there when you need them. I had one more question that I didn't answer about this last question, which was, what if it was, if this went up to 13 factorial plus 14? That would also be divisible by 2, because 14 is 2 and 7. Yeah, there's the question. 14 divisible by 2 and 7. So we're adding another thing that's divisible by 2 to this thing. Same thing is true with 16 and 18. Any even number that we add, the result is still going to be divisible by 2. And if we add 15 to this, then it's 3 times 5. So 3 times 5 would be adding another multiple of 3 and another multiple of 5, which means this new number would be divisible by both 3 and 5. This would be making the question a little bit tougher, so you probably wouldn't see it, but anything up to 16 is technically like doable. If they asked to 17, then we would not have a way to get there. It turns out that 13 factorial plus 7 is, or 17, is actually not prime, even though 17 is, because it's divisible by 211. But yeah, there's no way of knowing that without a calculator, or without being absolutely insanely good at dividing, and not for the GMAT. So great questions one and all. So that's the big takeaway here, is knowing these number properties well enough that it's just instant into your brain, right? Looking at way back at the very beginning, when we saw those four different questions, being able to look at these, know exactly what it's testing me on, and can start working with those number properties rather than just, testing a bunch of cases like we did. That'll get you to the answer, but it'll get you there slowly. So knowing these number properties can help you answer questions, whether they're easy, whether they're hard. One last question in the chat. Is it true that we won't get a hard question in the first quarter GMAT? No, that's absolutely false. If you get the first 3 questions right on this test, the algorithm starts to kind of freak out. And they're like, this person may never miss a question. We need to get them to miss a question. So if you miss the first three, if you make the first 3 or 4 in a row, you're going to get a really hard one. And then if you get that one right, you're going to get an even harder one. So yes, you can definitely get insanely hard questions really soon on quant and on verbal. And furthermore, it's not really worth trying to figure out whether the question is hard or easy. You just have to answer it, right? Do I have time to answer this in 2 minutes? If so, I'm going to answer it to the best of my ability. If not, I'm going to skip it. I'm going to move on because this might just be one of those insanely hard ones that shows up at any point. So that's all I have for today. Thank you for being here. Thank you for asking great questions. Thank you for participating. For being here, if this is your first Manhattan Prep GMAT Club presentation, just know that here's your code just for you, GMAT Club 75 $75 off of a complete course for GMAT, GRE, or for EA. Also, come to our site. We got a lot of great materials for all of these things. Also, the first lesson of our course is always free. So you can go to our site, look under free resources, and sign up for a free session 1, 3-hour session. Always free. We want you to come hang out, come join my class. And anybody at Manhattan Prep, we're happy to have you. And thank you for being here today. And thank you, GMAT Club, for having me. And yeah, this was great. Have a good rest of your day or a good sleep if you're in Sydney, Australia. Good night.